came down to Gulbarga University, and we are looking forward for, as our Vice Chancellor told, many more research collaborations with these scientists. He has about 16 years of experience in cell and tissue isolation, purification and cultivation. And in the past 15 years, he has worked, cooperating within multidisciplinary teams. As a result, he is here today amongst us. Thank you very much, Doctor, for your kind presence. I request you kindly accept the invitation and make your presentation.
Sir, please.
Please, sir.
Yeah.
Topic ಏನಿದೆ ಅವ್ರು ನೋಡಿ. ಇದೇನಾ ಟಾಪಿಕ್? Bio manufacturing and
Bio nanotechnology.
Hello, everybody. Thank you for joining us and helping me to check. You're changing the slides? Okay, it's top one. That's one. Is it back? Right. I'm going to give you a very short talk about bio-nanotechnology in regenerative medicine. You may know that regenerative medicine is a very interdisciplinary field of tissue engineering. What we're doing in tissue engineering and regenerative medicine is a really broad knowledge and a combination of different, very, very functional physics, mechanics, electronics, all the science coming together to help this regenerative design. Today I'm trying to give some topics about cell engineering and tissue regeneration and nanotechnology methods and design examples, some of them, and if the time allows them, about nanobiomaterials. And I don't think that the nano devices would be time for delivering this. So cell engineering and tissue regeneration is talking about improving and replacing biological function in an effort to improve clinical procedures for the damaged tissues or organs. So as we can see some of them, we try to treat this disease by not using directly medications rather than especially delivering some materials in the body to treat this disease. This is the tissue engineering, actually, or regenerative medicine is an interdisciplinary research. We start from isolating the cells, and then we make some, actually, starts from here, sorry. We start isolating the cells and differentiate or expand the cell numbers and enough some numbers that to be able to see seated in some kind of scaffolding, we call it. These scaffolding needs to be designed in a way that the cell can grow and interact and then demonstrate the same function as should be, and then it goes to we check this cellular and cell material interactions. In this case, materials are very important. Because our cells are in a micro level, we try to make this structure of the scaffolding to be able to cell to grow, to be able to cell migrate inside the scaffolding, and then after that we put in the design for a specific tissue regeneration, specific bioreactors, and we produce on a lab-grown tissues that to be implanted in the body. Within this space, we have to test the mechanical function of it. So as imagine if we want to make some skins, we make some skins, but the skin should be solid, should be elastic, should not tear, should hold the pressure or tension on the. This is the structure what we previously designed as. To achieve these goals, we need enough number of the cells. So expanding the cells is a big challenge. If we use the stem cells, we have to be able to make some exact differentiation of the cells. If you are using some primary cells that is directly biopsied from the patient, we need to expand it in monolayer, but then after that, very fast after that, something about 3 or 4 passage subculture. We need to grow the cells in a way that the cells behave the same as is in the body. That means every piece of cells, when we isolate from the body, when we biopsy the tissue, small piece of tissues, the cells recognize the environment and behave differently. So genetically change the characters, and that's a big challenge. We need to provide in a very short time, and as I said, about 3 or 4 subculture, provide an environment to the T cells to behave in a way that we need them. So, and another challenge is, should be enough. From 50,000, 100,000 cells, we may need 12 million cells. This is another challenge that are also not in monolayer. We need to culture and the 3D dimension to be able to complete our web. The cells must be able to differentiate, as we said, and for the desired phenotype. This is what we try it. So in 3-dimensional system, when we make it, it depends on the tissue regeneration, tissue type that we are working on it. It needs to be, the scaffold needs to mimic similar to the tissues. When we are doing when we want to produce any bone, for example, tissues, the scaffold should mimic the similar structure of the bone. If we are doing something with skin, then the scaffold should be so flexible, be elastic, and then should mimic the characteristics of the skin or cartilage, any tendons and so. So our reference is human body and the support for the tissues. And the cells need to be checked, the structure of the tissue which will regenerate, it needs to be checked. As I said, when we are regenerating any skin tissues, we need to make sure that this tissue has similar characteristics like skin. If we are doing some kind of muscle tissue for heart or cardiac muscles, we need to check them mechanically to see how is the tissue or is the structure is the same as the structure of the tissue itself. And also there are continuous some tests about cytotoxic tests, immune response, and biological risks that need to be all taken in account and tested. And then these are challenges, as we said. So as you can see here, so when we make any tissues, it needs to mimic the characteristics of the tissue itself. If it is on some kind of cartilage, for example, imagine the cartilage is about 2 millimeter thickness, and it holds over all weight. So 80 kilo in my case, so 82. In these couple of days, I put 2 kilo on. So 82 kilo, it needs to be held in 2 millimeter thickness of the cartilage, which consists from 80% water. That means 20% is extracellular matrix. The construct is so precise that it needs to hold together and smoothly and without any tension or pressure that can hold all these characteristics. This is very challenging part of the work. And also another part in the skin tissue regeneration is scarless tissue engineering. We have been successfully in the laboratory level. We could success that we designed an implant transplantation of the skin without scar. So we have checked the characteristics of scar tissue and normal tissue, this in case of skin. Then we could construct these biomaterial, this scaffold, that in the way that doesn't appear any scar on the body. So flexibility, functionality is also some kind of challenge. That we check case files. So this scaffolding that we're talking about, the best scaffolding which we can find is extracellular matrix. This is what we have. We insist on it. So for mimicking similar to the scaffold to extracellular matrix, this is what we design our scaffolding system. So we need to understand about histology of the tissue. We need to understand the cellular function. We need to understand genetic. We need to understand how the body functions, muscle force, and mechanical force of the muscle, load bearing of the tissues, depending on what kind of tissues is. In case of neurons or brain, we all need to understand how the cell signaling functions. So this case, after all this, we need to check whether our production mimicking the natural protein of the body, the natural protein of the scaffolding or not. Very simple case, in this case, which is in the cartilage and tendons and ligaments. These are made at more than 80% water. But we can understand, we need to have understanding about physics to see how these hydrogen bond and chemicals, hydrogen bond is functioning to hold the water molecules inside, bind together in the what kind of core protein which is called hyaluronic acid. These can combine together with lots of water. They can draw these lots of many hydrogen bonds. It's so strong. This is the case. This is the key point that how this structure of this cartilage can be stable, can hold together without splashing, without getting apart. So this is the main problem of this case of the hydrogen bonds. So all these needs to be taken account to design this scaffolding that the cell can interact with these like neuron cells or any kind of bone tissues that the cell can grow, or also the structure that we make in these cases, the nanofibers, cell can attach to this nanofiber properly to be able to grow and produce own extracellular matrix. So when I look on the time, before I go forward, let me go back. So the material what we're using, it should be biocompatible. I just want to delete biomaterials. Everything that we use is anyway biomaterials. It can't be without biomaterials. So biocompatibilities depend on what kind of tissue we are working with. We can choose some biopolymers, some biomaterials that are representing skin tissue, but these cannot be functional in the case of bone tissue. So biocompatibility is that we need to choose our material very precise, mimicking that the tissues function. The property what we also talked is biocompatible, and we can see how the biocompatibility is. It could be different. We can produce this in different ways. We could use also in the silk form in some kind of nano or woven material, nanomaterials. We can use as carbon nanotubes to trick and especially for the cell signaling procedures, freeze drying, and so they can be ceramic material or polymers, metals or polymers. In some cases, most of the cases, they are biodegradable. That means in a time they should disappear. They should be crude in the body because if we want to have proper tissue to replace that. So there are some mechanical challenges. We need to check the strength of the material, the elastic modulus of the material, the thickness, shear stress. All these is required before we suggest the product could be implanted. Apart from cellular level, we have to do on the mechanical test some kind of tension in case of skin. In case of cartilage, we need to have the rheology to see is it when in the body that both bones are over each other, are they of the wearing to each other? Then it goes to the rheology test. We have to have it in case of cartilage and also bones, about the compression load and also indentation. In some cases also for the nervous system we need to check this conductivity of the material. The best biomaterials what we can go to is our natural biopolymers. Natural polymers, they are collagen, glycan, alginate, sodium oxide. So actually, if we really look, the cell biologists, they know we are made of polymers. Everything what we could have made of is polymer. So most of the case that polymer is not plastic itself only. Polymer is, collagen is polymer, and it's kind of protein which is polymeric. So all we are made of polymers. than different kind of other polymers which come from the nature. So we can use as a biomaterial and biocompatible for the case of the different cases. And as example, collagen has excellent characteristics. They have excellent bonding together and binding to the molecules. Some kind of, when I walk, my movement is mainly, without collagen, I can't walk, I can't talk, because the cellular connection and interaction with the cells and proteins and extracellular molecules, it helps me to grow, to walk, and to talk. So this is is one of the most important biomaterials which we use in tissue regeneration or regenerative medicine. There are some synthetic biomaterials, although they are synthetic, but they could be corroded in the body. They could be, we tested the level of the corrosion or the biodegradability. Any tissues or any scaffold we design, before implanting, before suggesting to the implantation, we need to analyze how long will it take in the body that this disappears. Is it for 1 year, if it's 2 years, if it's a couple of months? So these are biodegradable materials, some of them, that we could use for tissue regeneration. They have different various use in the nanotechnology. So what we are doing, we make nanofibers, nanomembranes from these materials. We load our drugs or biomolecules extracted from, in this case of what we are doing here with Gulbarga University, we extracted some biomolecules and loaded on these nanofibers that we made, and we could see that how it functions. In one of our works is we could analyze here, as you can see, how scar tissue works. So we looked on inside the skin to see why we get scar tissue, and there's no hair growing on the scar tissue, is red and is bulky, is it's a bit hard. So we checked that. We found out that the main problem is lied by collagen fibers. The collagen fibers are normally in the skin similar like that. So they are in the dark areas. There are gaps, which call it pores. These gaps allow that this hair can grow, nerve cells can grow, blood vessels can grow. In case of the scar tissue, the collagen fibers are so tied to each other, it stops any blood flow or any hair growing in this case. The hardness of the scar tissue and the collagen fibers together cause that this scar happens. So I am one of my team members at the University of Bradford. I'm trained to align the protein collagen fibers in a way, not as a scar, in a way that I need to be designed. So one of the methods are this nanotechnology. We make the nanomembrane with different kind of collagen or combination to be able to seed the skin cells, make an artificial skin, and that could be implanted instead of scar site. How many? 2 minutes? So,
Kindly conclude, sir.
Okay. I very fast jumped the nanotechnology models. This slide goes. So, the way we are using it in our laboratory is electrospinning method. We combine biomolecules or drugs with the composites, with the biopolymers, and then we make some kind of membrane in a nano shape. And we can structure. This is done by my colleague with the collection of Sheffield University, and they analyze for corneal tissue engineering. And this is what one of my student project is. We deposit these nanomembrane on a surface and for different tissues. So the methodology is the droplet it becomes thinner and thinner within a very high different potential voltage. It's about 20-25 kilovolts. So it's very, very high precise. That particles which comes like this. So the particle, the droplet comes these polymers with all these drugs. Before it reach dropping down, it becomes nanofibers because of the electrode. The high voltage pulls the material over each other and makes some nanofibers and deposits to the surface or on the membrane. This is some samples of our work, and because of time, I just jump. These are some scanning electron microscopy of the membrane that we made for muscle tissue regeneration, and some tests that's done, some mechanical tests. The mechanical test is done within Mach 1 systems. It can pull, push, turn, and then do some different shape of in the case of the test. We can see in the tension and compression, we can see that the material is stable and the same in the sun sometimes, and is no disruption or corruption of it. So in conclusion, we say we use chitosan for our project with the Gulbarga University to design an bone dressing with embedded drugs isolated by biomarkers from plant by Professor Vidyasagar. We deposit these drugs to the nanofiber which made it, and we have tested some of this membrane, and they have got excellent swelling characteristics because it needs to have some capacities, water absorption because it would be in a body that needs to be not dried out and so and appropriate degradation that depends on the level of the chitosan and polymer. We can arrange and match what kind of tissues we want to treat depending on the tissue type. Thank you very much for your patience. Sorry for a fast speak. Thank you.
Thank you, Dr. Behruz Kaghani.
Thank you.
Dr. Behruz Kaghani delivered a wonderful talk on bio-nanotechnology in regenerative medicines, that is tissue engineering and tissue regeneration. He also explained the importance of that is the polymers, scaffolding natures, and in the production of nano compounds. Doctor, I have one question. After electrospinning, whether the weight of the nano compound increased or decreased?
After electrospinning, after electrospinning, depending on the level of ratio of the biomaterial, drugs and biomaterials, it could be the drug release is checked before transplant any implant, and we analyze how long will take that the biopolymers, whether in the body, will disappear and replaced by the extracellular matrix for the cells. That means the biomaterial what we're using, it should trick the cells to produce own extracellular matrix.
Okay, thank you. Thank you for a very lucid presentation.
Thank you.
And some of the methodologies you showed in the slide, they were of great interest. And we will be very happy, Gulbarga University will be very happy to continue the collaborations that you have already with Dr. Vidyasagar, further it with other scientists also, so that we will end up in a tangible good result to serve the society finally. Very interesting results you have presented. Because of the time constraint, because 2 o'clock Bradford University Vice Chancellor is addressing, that's why we had to stop a little, reduce your time a little bit. Kindly excuse me for that.
Yes.
Thank you very much.
Thank you. One of our aim is to hopefully we can bring this technology here to this Gulbarga University to produce this nanomembrane here at home. Thank you.
So now I request Professor Raja Saab and Professor Krishnan to present a memento to Dr. Behruz Kaghani.
Hello. If the Vice Chancellor of Bradford University is online, please get, if she comes on the screen, we will introduce her to the audience.
Hello delegates. Those of you who require return assistance for travel towards bus stand or railway station may contact Mr. Gurnath, the volunteer. His contact number will be displayed outside.
ನೀವು ಮಾಡ್ತೀರೋ ಅಥವಾ ಮಾಡ್ತಾರೆ ಇಲ್ಲಿಗೆ ಕೊಟ್ಬಿಡಿ ಅದೇ ಅವ್ರಿಗೆ ಗೊತ್ತಿರ್ಬೋದು. ಓಕೆ ನೋಡ್ಕೊಳ್ಳಿ ಅವರು
Is this common? Hello?
Hello.
Hello?
Hello. Good morning. This is Professor Vidyasagar.
Good morning. Can you hear me?
Yeah, just a minute. Just 2 minutes. So our Vice Chancellor is coming.
Hello.
Hello, good morning.
Yeah, good morning, and it is good afternoon from India.
Good afternoon.
Professor Shirley Kannan, thank you very much for your gracious presence. We have almost about 300 delegates here in this international conference which is being organized by Gulbarga University, with joint collaboration of your university, that is University of Bradford. We wish and we are eagerly waiting for your words on this occasion. You know very well, when we met for the first time about 3 months back at your institute, you are assured that you will be here in India with us Anyway, hope to see you next time physically at our institute. I extend a warm invitation also through this phase. And straightway I would request you, we the audience are eagerly waiting for your message in view of this international conference. I welcome you once again, Professor Shelley Kandom, Vice Chancellor, University of Bradford. Over to you, ma'am.
Thank you. Thank you so much. Thank you for that introduction. I want to start by giving very special thanks to the Vice-Chancellor of Gulbarga University, who has really been behind this initiative significantly. Professor Dayanand Akskar and all his colleagues have been extremely excited about this initiative. And I did promise that I would be in India, and I will be. This year we need to make sure that we meet in person. So, distinguished guests, ladies, gentlemen, esteemed scholars and participants from across the world, I would like to start by wishing everybody a happy and peaceful New Year. Here at the University of Bradford, with all of our partners, we are really hoping that we can contribute to ensuring that across the world we have people living in more settled and peaceful societies. And on behalf of the University of Bradford, I want to give a warm welcome to the International Conference on Recent Advances in Bio-Nano Composites for Improving Human Health. They cannot be a more important topic. How can we improve human health through the most significant and cutting-edge advances? And this conference will focus on this very matter. It is indeed a great honour to be here as we embark on our joint journey to explore the latest advances at the intersection of biology, nanotechnology, and composite principles and properties, with a particular special focus on the potential, as I say, for the benefit for human health across the globe. And as we gather in this virtual place today, we find ourselves at the intersection of a scientific innovation at the technical frontier, where innovative interdisciplinary collaborations are poised to reset the way we understand diseases, how we diagnose them, and how we treat them, to make sure that human health problems are prevented and treated in very, very different person-centred ways. The merging of biology and bio-nanotechnology has opened up and will continue to open up a new episode of possibilities, and this important conference serves as a hub for the exchange of ideas that will certainly shape the future of healthcare, and our respective universities and our esteemed academics are leading the path to this change. The theme of our joint conference, the exploration of plant and microbial molecules and the design of bio-nano composites for human well-being, reflects the overall goal of integration of nanotechnology and composites into the complex web of biology, as I say, to improve human well-being. And this conference will serve as a significant platform to stimulate further dialogue, to share leading-edge research and foster partnerships that advance healthcare. And over the next 2 days, we will have the privilege of hearing from professionals and academics who have dedicated their lives to expanding the frontiers of knowledge in this field. And sessions, as you will have read, will range from the design and synthesis of innovative biomaterials and their application to microbiology, infections, cancers, skin care, tissue engineering and regenerative medicine, diabetes, as well as other complex conditions. It's a testament to the endeavours of everybody that is involved in this field and in this conference. And I've been told that the beauty of this conference lies in the equality, diversity, inclusion, of international and inter-transdisciplinary platforms for the exchange of ideas. Nobody can achieve anything on their own, and this indeed is the era of collective collaboration. Everything must be about partnerships, or we will not be successful in addressing these global challenges. I'm hoping that we will be able to use this platform as an opportunity to connect with more colleagues, to share more ideas, to develop collaborations that will place us at the leading edge of global collaborative work in this field. We are on a shared intellectual journey, and let's be inspired by one another and the potential of bio-nano composite materials to revolutionise healthcare. Collectively, our efforts will reshape the future and make it more personalised, effective, and indeed accessible to all. I want to thank particularly the British Council and Karnataka State Higher Educational Council for bringing us together from our initial meeting in Bradford, for bringing the scientists from the University of Bradford and Gulbarga University together on this joint research project. And I wish all of our academics and scientists who are involved great success in this significant milestone in the treatment of what I have heard about in terms of the treatment of diabetic skin ulcers. Once again, thank you to the Vice-Chancellor of Gulbarga University, Professor Dayayand Agskar, and all of the participants. And I hope this conference will be successful in sparking new ideas and stimulating our creative juices. I wish you all a great success, and once again, I am looking forward to seeing and meeting you all in India. Thank you.
Thank you very much, Professor Shirley Kandom. As you rightly said, in the intellectual journey of Gulbarga University and the University of Bradford, we have much things to be achieved in the days to come. Hope both the universities must thank the British Council and also the Karnataka State Higher Education Council for their valuable support with this joint collaboration. I would like to say that Professor Behruz Khagan is very much here, and he is going to be here at our campus for another couple of weeks, where he will be continuing his collaborative project research with Professor G.M. Vidyasagar. I only hope there will be very good, significant outcome of these collaborative programs, and we can meet in the next days to come. Thank you very much.
So now we'll have a break for lunch, and after lunch we'll again reassemble in this hall at 3 p.m.
डिस्टर्ब हुआ तो रहते सर आपके साथ
वहीं पे
Hello. So now we are continuing the technical session 1. I request all the participants to come inside the auditorium.
अलीगढ़ बस जी 23 years in NCL and from 2017 till today I am in AMU founder director and I'm the founder director of nanotechnology. Yeah, so this is founder only and अभी अभी हमने established center of nanotechnology, interdisciplinary center of nanotechnology, and now we are doing research, teaching, and MTech in nanotechnology. मैं तो permanent position. अभी मेरा 29 में रिटायरमेंट है वहाँ से. तो I am established. They called me to establish a center, तो मैंने कर दिया. तो अभी मैं जी ये इसको ऑन कर देंगे. नहीं बिल्कुल. हेलो, आवाज आ रहा है? नहीं, कोई बात नहीं.
Good afternoon. Your attention please. Good afternoon everybody. Now we are in the post-lunch session. I request all of you please have your seat and we will start the post-lunch session. The first speaker in the post-lunch session is
Pointer.
ಗೊತ್ತಿದೆ ಅವ್ರೇನೋ ಮಾತಾಡ್ತಿದ್ದಾರಲ್ಲ. ಆಯ್ತಾ? Okay. Professor Dr. Afzar Ahmad. If it is permitted here, I will say that I know Professor Afzar Ahmad last 20 years. When I was in Gulbarga University, we came across Professor Afsar Ahmad. He was working in NCL Pune. He was one of the pioneer workers in nanomaterials, especially from the chemistry background. Later he switched over to bio-nanomaterials also. And he was a big name during those times also. Imagine now. We invited him to Gulbarga University for a conference, and even to microbiology department, and our biological science departments called him as BOS member several times. So he is closely associated with us, Gulbarga University, by life science departments, in one capacity or the other. Professor, after working for about 15 years in NCL Pune, National Chemical Laboratory Pune, in 2017 he was selected as full professor in Aligarh Muslim University. Since 2017, he has been working in Aligarh Muslim University, continuing his work and visiting almost all countries in the world as well as different parts of India to promote the knowledge and research on nanomaterials. He is almost, authority. And we used to identify him with the scientists of Indian Institute of Science also. So much of interaction they had those days. So he is here again in Gulbarga University, means our university is highly going to be benefited. We are fortunate that he could make some time, and I can tell his research in detail also, his work, but this is not the proper time. So I just welcome Professor Afsar Ahmad, Dr. Afsar Ahmad, and then probably he has to leave today. That's why we have given him a special time so that he will present his work. We will be benefited, and Dr. Dastagir has kindly agreed for that because he was to present now. His will be the second one. So I request Professor to kindly make your presentation. Maybe you can take about 15 to 20 minutes, sir, if you don't mind.
Thank you so much. Good afternoon to all of you. And thank you so much, Professor Raja Saab, for giving a nice introduction. I think we met around in 2012 or 13 in Bangalore. And after that, we contacted on so many times. First, I would like to thank the organizers for giving this opportunity, especially Professor Vidyasagar Saab and Professor, we, for the first time, when I visited here, Professor Dayanand Saab, now he's the Honorable Vice Chancellor of this university, he invited me for the first time at Department of Microbiology, and after that I had several visits. So now, since time is very short, now I'm going to talk on major breakthroughs in biosynthesis. For the last 23 years, I spent around 23 years at CSRNC here, Pune, and 2017 I joined as a founder director of nanotechnology at Aligarh Muslim University. Aligarh Muslim University now decided to establish a state-of-the-art nanotechnology center at Aligarh Muslim University. And we established a Center of Nanotechnology. Now we are running MTech Nanotechnology, Advanced PG Diploma in Nanotechnology, and PhD in Nanotechnology in full swing. Next slide. And now we are also running a DBT-sponsored project, Center of Excellence on Nanomaterials and Drugs from Endophytic Fungi, and we received around 4 crores from DBT in 2019. Next slide. And now, for the last 23 years, our group is mainly working on biosynthesis of nanomaterials using endophytic fungi, drugs from endophytic fungi, and recently we started the conjugation of drug to nanomaterials for targeted delivery. All the things from endophytic fungi, why? Because endophytic fungi, they are not toxic. Daily we eat dry fruits, vegetables, Then so many some other like fruits, vegetables, dry fruits, they are full of endophytic fungi, but they don't cause any harm. If you will cut an apple and if you will see under the microscope, then you will not eat the apple because that is full of around 25 endophytic fungi are there in the apple, banana, custard apple, sugar, then coriander, full of endophytic fungi, but they don't cause any harm. Therefore, we are using endophytic fungi for the synthesis of a range of nanomaterials, like metal oxide, sulfide, a range of nanomaterial we made. And then, Taxol is an anti-cancer compound. People are isolating from this plant, Taxus baccata. But the problem is that if you will isolate the Taxol from this plant, you will get only 2 grams of the drug. If you will harvest 100 years old plant, then you will get only 2 grams of the compound. That is sufficient to treat only one patient. Because if you will plant a Taxol with the help of seeds, it takes 100 years to grow. Then you will, and if you will harvest, you will get only 2 grams of the drug. That is sufficient to treat only one patient. So in order to provide the drug at low cost to the patients and low cost to the environment, I went to Srinagar and Darjeeling brought stem leaves flower of this plant at NCL Pune and isolated 40 endophytic fungi, and this fungus is producing Taxol. Now no need to disturb the biodiversity. And since we are making nanoparticle in our lab, drug in our lab, we made nanoparticle drug conjugate for targeted drug delivery. Next. And now a range of nanoparticle, like there are 5 types of nanoparticle: metal oxide means inorganic nanoparticle. Then organic nanomaterial like carbon, porous carbon, graphene dots, then solid lipid nanoparticle, then clay nanoparticle, polymeric nanoparticle, a range of nanoparticle we have synthesized with the help of biological system. Nanoparticle can be obtained by physical and chemical method. These methods are hazardous, eco-friendly, cumbersome, and yield big particles. Therefore, there is a growing need for reliable and economic synthesis of nanomaterial. In that direction, we have pioneered this area. Nanoparticles which we are making from the fungus and plant, they are water dispersible. Protein cap, they don't flocculate. Shelf life is very high. They are very cheap. They are not toxic. So now it is very, very difficult to make nanoparticle with the help of chemical physical method. But our approach is very, very simple. And now we can produce the nanoparticle in the bulk quantities. Till today everybody is making 1 gram or 2 grams. Then you are not going to solve the purpose. Now we have developed a method by which we can make the nanoparticle in kgs. And recently, just our team, both the sons, they established a company of nanomaterials. They are making nanoparticles, that nanofertilizer, a range of micronutrient and macronutrient. They are making with the help of fungus and plant extract only. We can produce in the bulk quantities. Next. And now we have screened a range of nanomaterials in our lab. Now we are screening our nanomaterials in healthcare, agriculture, environment, energy, water desalination, and as well defense. You know that nanoparticles, a range of nanoparticles which I made, we are getting very good results against coronavirus, against HIV and all, and against retina regeneration, cancer, malaria. Our expertise is in nanomaterial synthesis. Any type of nanomaterials we can synthesize because nanoparticle people are making at very high temperature, high pressure. Like we have made barium titanate. NCL people are making barium titanate at 1800 degrees centigrade. I made a room temperature. Copper aluminum oxide, 1100 degrees centigrade, again I made a room temperature. And after that we are screening in healthcare, agriculture, environment, energy. Energy means energy conversion, energy storage. Next. And now next. A range of nanoparticles we are making only from the endophytic fungi, not from saprophytic fungi, not from other fungi, only endophytic fungi because they are safe. Next. And then we isolated a range of nanomaterials and drug from the mushroom also. Next. A range of mushrooms, these mushrooms we collected from Himachal Pradesh. Professor Lakhan Pal is the authority on that. He is the father of mushroom in India. He gave several mushrooms and now we are screening our mushroom for the synthesis of nanomaterials. Next. And now range of mushroom next. And recently we just tried to work on the truffles. India is a big country, but which is a matter of shame. There is so far no reports of truffles from India. Truffle, very costly, they are underground fungi. 40,000 rupees per kg, but there is so far no reports of truffle because